In this video, I introduce a Dexterous manipulation world model. World models can learn environmental dynamics in latent space from observations and actions. Dexterous manipulation world model is designed to capture the fine-grained information required for precise dexterous control by predicting the future latent states of the environment, condition path states, and dexterous hand actions. An RGB image IKI at a time step KI for index I is observed by the agent. The latent state SKI encoded from IKI is computed by an encoder E5. Dexterous action taken by the agent is defined as AKI. A state predictor F state maps a current latent state SKI and action AKI to AKI plus 1 to the future state SKI plus 1 carried. As shown here, this dexterous manipulation world model. This input image and this the prediction of next state. This is the encoder and this decoder, this dexterous action and this change in camera pose. The state predictor F state uses these three as input to predict the next latent state as Ki plus 1 caret. An input image IKI is encoded by using a Dino V2 encoder E5 to latent embeddings, and the patch level features are defined as a state SKI. Action AK1 to AK2 is defined between two states SK1 and SK2, and each hand features are represented by 21 key points with coordinates HKI. The changes in camera translation and orientation are defined as delta T and delta Q, respectively. The hand action vector AK1 to K2 is defined as here and shown in these figures. The dynamics model alpha theta takes as an input a history of observed environment states from SK1 to SKN as shown here, and the current action AKN to Kn plus 1 as shown here to predict the next state as Kn plus 1 caret as shown here in this equation, where theta is a predictor's parameters. To predict the future latent state of environment, the mean squared error loss and hand consistency loss are applied to jointly train the model on a patch of P patches, as shown here, which consists of two terms. One is mean squared error loss, one is hand consistency loss, where P indexes the image patch and D is the dimensionality of the state. As shown here, this is a model of DexWM architecture. This is the predictor F theta. This is path observations. This is the actions, and this is the change in the camera pose. This is the prediction. And this is a decoder to reconstruct the input image, and this is the key point predictions. The mean squared error loss and hand consistency loss together are used to train the DexWM model. DexWM can be applied for goal-conditioned planning waypoint trajectories using the learned world model alpha theta. give an initial state S0 and a goal state SG, as shown here, this S0 and this SG. The planning problem is defined as here, where theta k represents the joint angles of a robot. G uses the forward kinematics of the robot to calculate the AK. C is the planning cost and T is the planning horizon. The cross-entropy method is used to optimize the joint angles. The planning cost is the sum of two losses, namely C state and C points, with the C state being the L2 distance between ST and SG, as shown here, this SG and this ST, and C key point, Euclidean distance between key point pixel locations corresponding to the two heat maps, VT Garrett and VG. As shown here, this start frame and this goal frame, this encoder here, this joint angles. Predictor uses this latent states and actions as an input to predict the next state. And this planning cost is used to optimize the waypoint trajectories, as shown here. For more details, please check with these references. Thank you. Bye.